The required task is to design both a column and beam for a residential building to be situated at Deakin Geelong for first year engineering students. A proposed layout of a 23 by 50 metre building is to be built using energy efficient materials whilst maintaining a beam and column structure. The physical significance of these locations meant differing load options had to be calculated over their respective tributary areas, and as the beam is on the outermost point of the structure, it is required to hold much greater loads than the central beam. There were many design challenges faced when creating the column design, the first of which was choosing appropriate loads for residential apartment, as floor, wall and slab loads had to be found using the Australian standards. After finding the dead and live loads, we were required to calculate appropriate tributary areas and therefore find appropriate uniformly distributed loads. From this, we were then required to find a material with a large enough cross-section to be able to withstand the compressive forces required. After research, a high-strength composite concrete was found that included steel fibres throughout its design to increase strength and ductility. This was explored as a final material choice, although the increased strength meant that the cross-sectional area was to be too small and would jeopardise the column's reliability. From this, reinforced concrete was looked at as it provided increased strength and ductility whilst maintaining low manufacturing costs and environmental impacts. Reinforced concrete uses steel rods placed throughout the column, and these rods are made from steel of a required diameter. My final design used N12 rebar, as anything greater meant that concrete would be taking less load and therefore require a smaller cross-section. Although this is a positive, it again meant that the cross-section would be too small to be plausible. Therefore, N12 rebar was added to a 30 megapascal concrete to find the ultimate design. The concrete was said to be poured in a 255mm square with 4 steel rods in each corner as shown in the visual. In the modern age, steel I-beams are a major part of any large structure as they provide exceptional tensile and compressive strengths. They are used commonly throughout beam design as they provide high shear strength and durability through their ductile nature. From this, they are able to withstand high winds, storms, and natural disasters. Compared to timber, steel doesn't wither or rot and is able to hold against time. Although for these reasons and manufacturing processes, steel beams come at a greater cost than concrete or timber. I-beams are also sustainably friendly as they are made with little byproducts and can be made from scrap metal, reducing raw material collection. I-beams are used specifically as the web section resists shear, whilst the flanges resist the bending moment. I-beams are very efficient in resisting these forces whilst maintaining lower weight, cost and cross-sectional areas. The design challenges faced were that the beam was located on the outermost edge and was required to hold greater loads. This meant it had to have a larger cross-section and required a greater ability to withstand shear stress. Following research and calculations, the cross-section of the I-beam was chosen as follows in the image.